Hello everyone. In today's lesson, we're going to learn about central angles and inscribed angles, and discover the relationship between them. Let's start with the first figure. Here we have a circle with radius r. Notice that both angle alpha and angle beta subtend the same arc, CE. So, what's the difference between these two angles? The difference is where their vertices are located. Alpha is a central angle, which means its vertex is at the center of the circle. Beta, on the other hand, is an inscribed angle, meaning its vertex lies on the circumference of the circle. Although they are different types of angles, they both subtend the same arc, CE. Our goal is to prove that the inscribed angle is exactly half the central angle. In other words, we want to show that alpha equals 2 times beta. Now let's look at triangle D1AE. Since D1A and AE are both radii of the circle, the triangle is isosceles. Therefore, its base angles are equal, so beta equals gamma. We know that alpha plus delta equals 180 degrees. We will show you this later on this video. We also know that the sum of the angles in any triangle is 180 degrees. Therefore, beta plus gamma plus delta equals 180 degrees. Since beta equals gamma, we can write 2 beta plus delta equals 180 degrees. From equation above we become delta equals 180 degrees minus alpha. Now look at the figure again. Now substitute this into the previous equation. 2 beta plus 180 degrees minus alpha equals 180 degrees. After simplifying, we get 2 beta minus alpha equals 0. Therefore, alpha equals 2 beta. So we've proved that the central angle is twice the inscribed angle in this special case. Now let's move on to the general case. In this case, neither side of the inscribed angle needs to pass through the center of the circle. The only requirement is that the central angle and the inscribed angle subtend the same arc. In the figure, angles epsilon and zeta both subtend arc BF. Here, epsilon is an inscribed angle, and zeta is a central angle.
Our goal is to prove that epsilon is half of zeta. From the previous proof, we already know that if one side of an inscribed angle passes through the center, as angle theta does in this figure, and theta and the central angle eta subtend the same arc, then eta equals 2 theta. We can also see from the figure that eta plus zeta equals 2 times the quantity theta plus epsilon. Now replace eta with 2 theta. 2 theta plus zeta equals 2 theta plus 2 epsilon. Subtract 2 theta from both sides, and we obtain zeta equals 2 epsilon. This is exactly what we wanted to prove. So, in every case, the central angle is twice the inscribed angle, as long as both angles subtend the same arc. To better understand the inscribed angle and the central angle, we use this figure. In this figure, as you can see, we have a red circle that contains three inscribed angles F, C, and H. These inscribed angles have one thing in common, and that is the arc EI. We have proven that an inscribed angle is half of the central angle subtending the same arc. In this figure, angle J is a central angle, and it has the same common arc as these three inscribed angles. The central angle is now 53.2 degrees, and the three inscribed angles, namely angles F, C, and H, are all equal and each one is half of the central angle J. The amount of each of the three inscribed angles is 26.6 degrees, and the central angle is twice that value, which is 53.2 degrees. Here, we can observe that by moving either of the 2 points E and I on the circle, these three angles remain equal to each other, although their amount may change. They are always half of the corresponding central angle. On the other hand, when we move point F on the circle, we observe that the inscribed angle F does not change, because the opposite arc remains constant. If we move any of the points that form the inscribed angle along the circle, we can still see that the amount of the angle does not change. Now let us see why we say that the angle of a straight line is 180 degrees. At the beginning of this video, we mentioned that at the end we would show a simple way to understand why the angle of a straight line is 180 degrees. Here, you can see a circle. The center of this circle is point A, and AB is the diameter of the circle. The angle CAE in this figure is 144.2 degrees. We know that the diameter of a circle divides the circle into two equal halves. We also know that a complete circle has 360 degrees. Therefore, when the diameter divides the circle into two semicircles, each semicircle has an angle of 360 divided by 2, which is equal to 180 degrees. Now we move point C along the circle toward point B. We can see that the angle changes, and when point C reaches point B, the angle becomes exactly 180 degrees. Therefore, a straight line creates a 180-degree angle. The angle above the line is 180 degrees, and the angle below the line is also 180 degrees. Now, as we mentioned at the beginning of the video, the sum of the interior angles of every triangle is 180 degrees. In this part, we want to show the reason behind this fact. In this figure, you can see a circle with a triangle inside it. This means that all three vertices of the triangle lie on the circumference of the circle. The three vertices are labeled B, C, and D, and each one creates an angle inside the triangle. At the bottom of the figure, we have shown the sum of these three angles. In this example, the angles are 76 degrees, 45.5 degrees, and 58.5 degrees. When we add them together, the result is 180 degrees. Now, we move point C along the circumference of the circle. We can see that the sizes of the three angles change, but their total remains constant and is always 180 degrees. There is also another simple explanation for this. Each angle of the triangle is opposite an arc of the circle. For example, angle B is opposite arc CD, angle D is opposite arc BC, and angle C is opposite arc BD. These angles are called inscribed angles. We know that an inscribed angle is always half the measure of its intercepted arc. Therefore, if we add these three angles together, we are actually adding half of all the arcs of the circle. Since a complete circle measures 360 degrees, half of the circle is 360 divided by 2, which equals 180 degrees. So, the sum of the three angles of a triangle is 180 degrees. In this dynamic example, we can clearly see that when the position of the vertices changes, the individual angles change as well, but their total remains unchanged. Therefore, we can conclude that the sum of the interior angles of every triangle is always 180 degrees. We also know that for every triangle, we can draw a circumcircle, that is, a circle passing through all three vertices of the triangle. Since this result is true for every triangle placed inside such a circle, it applies to all triangles. Therefore, the sum of the three interior angles of every triangle is always 180 degrees.
If you enjoyed this video, don't forget to like, subscribe for more math videos, and share it with your friends. I'd love to hear your thoughts, so leave a comment below. Thanks for watching.